Good afternoon. My name is Maria Kolishuk, and on behalf of my co-authors Olga Tichuk and Andrei Yefimenko and Yuri Rusinsky from Zhytomyr Polytechnic State University, thank you for the opportunity to present our work. Our paper is an experimental study of how the BGP protocol behaves in a multi-protocol virtualized environment built with a GNS3 emulator. In short, we built a reproducible dual stack testbeds and measured with statistics how MP-BGP convergence and how stable it stays under four controlled failures. BGP is the backbone of the internet. It provides connectivity between autonomous systems, modern networks, combined virtualization, multi-protocol support, and traditional infrastructure, which raises both routing instability and convergence time. The stability of MP-BGP underpins data center, interconnects financial transaction, cloud platform, and government communications. Even brief instability causes service degradation. The threats are also growing, BGP hijacking and route leaks. The Pakistan YouTube incident showed how a single one announcement can predict global traffic and routing instability during the Russo-Ukrainian war, together with the fragmentation of the Ukrainian connectivity segment since 2014, intensified after 2022, demonstrates the vulnerability of inter-domain routing under adverse conditionals. Three gaps remain. Most experimental work targets homogeneous single protocol IPv4 networks, so the joint behavior of MP-BGP running IPv4 and IPv6 at the same time is largely unquantified. Individual aspects, convergence, security, anomaly detection, filtering are studied in isolation, and reproducible test beds are really combined with explicit measurements of the convergence versus stability trade-off. Our position, to our knowledge, is no prior study jointly evaluates MP-BGP convergence, dual stack failover, policy filtering, and channel instability within a single reproducible GNS3 testbeds. The aim of the work is to quantify the convergence and stability trade-offs of MP-BGP under four controlled failure models is reproducible dual stack GNS3 testbeds. We make a four contribution. First, documented reproducible testbeds with versions, license, and resources state. Second, the first joint advanced lowering the keep alive timer below 5 seconds, triples flap frequency while convergence gains diminish 9 repetition per scenario. Third, an 87% reduction of inbound prefixes through the roadmap at no convergence cost. Fourth, three actionable configuration guidelines. Everything runs in GNS3 version 2.2.45 on Ubuntu 22.04. We deliberately use three independent open source BGP stacks FRR routing, BERT, and YOS. So the observed behavior reflects the protocol itself rather than one vendor. FRR and BERT run as a Docker container, YOS as a virtual machine. The network is genuinely dual stack. MP-BGP carries both IP version 4 and IP version 6 prefixes over 30 and 64 links. Convergence time defined precisely from the withdrawal of an active route to the installation of a new valid next hop uh, confirmed by data plate reachability. Every scenario is repeated 9 times, and we report the mean with a 95% confidence interval from students to disruption. The diagram shows seven autonomous systems. AS65002 acts the transist core for routers in a full mesh IBGP topology. Every link is dual stack with parallel IP version 4 and IP version 6 sessions carried by MPBGP. A backup BGP pass-through AS65004 protects the main links between AS65002 and AS65003. The four numbered makers on the diagram correspond to the four scenario link failure, IP version 4 to IP version 6 failover, router map filtering, and the flap effects. This is a channel flapping. Scenario 1. We disabled the main link from AS65002 to AS65003. The prefix 8.8.8.8 32 was withdraw router R2 switch to the backup path through AS65004. The routing table updated within 4 to 6 seconds and the session stayed stable. Scenario 2. Parallel IP version 4 and IP version 6 YBGP sessions run on the same physical link. We shut the IP version 4 interface. The IP version 4 sessions went to the active state while IP version 6 remained established. Connectivity was restored over IP version 6 within the within 1 to 2 seconds with no administrator intervention, and that is the practical value of MPBGP. Scenario 3. We applied a prefix list and a filter in router map and bound on the neighbor. The number of accepted prefixes dropped from 31 to 4 and 87% reduction with fewer update messages and no session disruption. A scenario for a script toggled their link every 10 seconds. The session cycled through established, idle, and active. Each flap triggered table updates and reprocessing of attributes. SMP showed periodic loss with RTT speaking and then stabilizing. This leads us to the key finding. This is the head of paper. The graph shows RTT during flap under 2 time settings with the standard value, keep alive 60 hold 180, recovery is shown with aggressive value, keep alive 5, hold 15. It is much faster. For the flap scenario, lowering keep alive from 60 to 5 seconds cuts per cycle recovery by 76.7%, from 7.5 seconds to 1.75, but there is a price that some reduction triples flap frequency from 1 to 3 sessions resets per 10-second cycle. So the operational boundary is clear. No unstable links keep alive at 10 seconds or more, and only lower it to 5 in stable high availability environments. All of three different exceed the 95% confidence interval, so they are statistically significant. 9 repetition per scenario link failure averages about 5 seconds. Dual stack failover 1.5 seconds. Router map filtering exactly 2 seconds with zero standard deviation. Flap recovery 1.75 seconds. The variance is low throughout. The standard deviation never exceeds 0.47 seconds. So the behavior is stable and repeatable. Every value falls within the ranges set by RFC 400 2071 and RFC 400 7060, and much prior literature. Roundly 5 seconds for links failure and about 2 seconds for filtering. Three practical guidelines follow from the results. First, turn the timers to the environment. Keep alive 5 to 10 seconds is optimal for stable, high availability networks. Second, filtering and bound routers by default. In our course, this removed 87% of prefixes at zero confidence cost. Third, where link stability is not guaranteed stable, the network with carefully turned times and operationally valid dampening. Not the default routing flap dampening values, whose limitations are documented by the RIP routing working group. And not on limitations. GNS3 is an emulator. It does not reproduce physical layer effects, so our numbers describe control plane dynamics under ideal conditions. 9 repetition are adequate for a deterministic setup, but flapping would benefit from larger samples. The routing table held 31 prefixes, for fewer than real tables for over a million prefixes, yet the 87% reduction is protocol level effects and should generalize. For future of work, we plan to compare BFD at pass and prefixes independent convenience against time and turning. To calibrate RFD parameters for dual stack, to apply machine learning to convenience time series for early detection of DOS, and hijacking, and to integrate the test bed with monitoring system on the path toward self healing routing domains. To conclude, reducing keep life below 5 seconds yields diminishing convergence claim, while tripling instability in bond filtering at an 87% reduction cost nothing in convergence term. MPBGP failover from IP version 4 to IP version 6 completes in 1.5 seconds without intervention. Our main contribution is reproducible, fully open source GNS3 testbed that links convergence configuration actions to measurable control plane outcomes, and it is first join evidence of the stability convergence trade-off under dual stack operation. Thank you for your attention.